So our next speaker is Mika Hatanpaa from Nokia. He's the head of R&D, in particularly focusing on mobile networks, both central, regional, and edge data centers. He also joins us from Finland.
You're using this one. Zoom. Okay, should we wait for the time? No. Okay, it's time, so I will start. So, good afternoon, everyone. So, my name is Mika Hatanpaa, and coming from Espoo, Finland. And the topic for this presentation today is architecture options for Cloud RAN VDU. And yes, I will first start by a bit explaining what is VDU and what we are doing there. So, overall, we could say that the Cloud RAN, or let's say radio access networks, or RAN as I call it, abbreviated here, we have been traditionally using purpose-built hardware for a very long time, since the early days of these radio access networks that are built since the times of GSMs and even before that, from late 90s. Also, but recently we can say that Cloud RAN has become a viable option in implementing the radio access networks, and mainly due to advances in technology. And what I mean with the advances in technology is really about the more capacity or higher capacity server platforms, higher capacity CPUs, higher capacity capabilities of the CPUs to actually process the radio functions themselves. And then in this presentation, I will briefly introduce the Cloud RAN architecture first, and then I will cover some of the deployment options of the virtualized distributed unit. And then I will also discuss about this acceleration functions required to actually efficiently process the layer 1 functions of the radio baseband processing. And I will focus on the Open Edge hardware platform. So Open Edge is the kind of a Nokia solution or Nokia native solution that we have contributed to OCP already earlier, and then we are now kind of utilizing that as the main vehicle and the main platform for the Cloud RAN deployments together with the accelerators. First, briefly about the Cloud Radio Access Networks. So Cloud RAN, briefly what it is, what it consists of. So I would say that there are three main parts in this Cloud RAN. So first of all, of course, we need to have the radio units that are then communicating wireless with the end users, or UEs, user equipment. Then we have the virtualized distributed unit, which is the baseband processing unit, typically located, I would say, maximum 20 kilometers away from the radio units, simply because of the latency requirements of the radio processing stack. And the VDU then processes the real-time parts of the baseband stack itself. So mainly the layer 1 PHY layer, as well as the layer 2 real-time functions like RLC and MAC. Then the third part of the architecture is VCU, which is then doing the non-real-time processing of the baseband, basically of the packets coming from the radio and going towards the radio, and we typically call these functions are then called the PDCP layer, as well as the RRC, or radio resource control layer there. And for both of these, we would typically utilize the Open Edge as the platform for building the kind of cloud platform, first of all, or cloud infrastructure, and then running the container applications on top of that one. The location of the VDU and VCU actually can vary in the network, so we can locate those on the cell site. So we call that the DRAN deployment, so distributed RAN deployment, where both where the VDU is located next to the radio unit on the cell site, and then the VCU can be in that case located much further away. So in this case, for example, showing that it could locate in this edge or regional edge data center that could be even up to 100 kilometers or a few hundred kilometers away. And the reason for kind of separating VDU and VCU functions to a separate entities is simply because that we are targeting to have pooling gains, and where we can pool more of the capacity into a larger VCU function, we can then actually gain in terms of efficiency and total cost of ownership of the solution. Then the next option here is this kind of first CRAN deployment, where we could locate the VDU function in a far edge data center. But here the laws of physics then kind of say that we cannot locate it further than about 20 kilometers away because of the kind of round trip time latency requirements because of the processing. Then VCU again can be a bit further away in regional edge data centers. And then the third option that we see is such that actually then VDU and VCU could be co-located both in this far edge data center. And maybe one option that is not shown here is also what we are seeing quite a lot as a requirement from customers as of today is a kind of co-located deployment where VDU and VCU are both actually located in the cell site, which would be the traditional way that how actually baseband has been implemented with the purpose-built hardware in the past. There number of sites, there's some characterizations shown here. Basically, we have a lot of cell sites typically in a large network. It can be tens of thousands. then the far edge sites much fewer, so we try to kind of centralize the processing into those sites, and then less and less of the edge sites there, and that's kind of also the size of these, I would say, micro data centers or edge data centers is typically very small. In the cell site, we talk just about a couple of servers, and then in the far edge sites, it could be a few racks of servers, meaning basically some tens of servers, and then in the edge, of course, it will be can be a much larger installations in order to pool the capacity there. Okay, then about the acceleration. So acceleration is something that we would utilize, and with what we need to utilize in the layer 1 5G physical layer 1 processing of the fronthaul interface, so basically processing the packets when they come from the radio, and that is a very resource intensive task as such, and I would say that the traditional CPUs don't actually perform that very well, so they are not good in doing that kind of processing what the layer 1 requires. Therefore, it makes sense to use an accelerator that is more purpose-built to actually accelerate the key functions of the L1 processing. And that then also frees the expensive CPU resources, so basically freeing CPU cores for other tasks instead of this very resource-intensive layer 1 processing. The accelerator functions are typically implemented with PCIe cards or add-in cards that are then connected to the CPU. Typically, we could have one add-in card for kind of the layer 1 acceleration, but I would say that in a larger installations, it actually makes a lot of sense to have more of the accelerator cards in one server than just one. Basically, then kind of having, for example, 3 accelerator cards and attached to one single CPU as such. And then there are different ways of doing the acceleration or layer 1 processing in Cloud RAN in general, and I would say that everything started with this approach to actually do kind of local-side acceleration, so that basically only selected functions of the layer 1 processing are accelerated. For example, the forward error correction or LDPC in 5G networks. That would be then accelerated by a PCI card. And then the other option is the inline acceleration, which is kind of similar that how it has been done traditionally in purpose-built hardware, that the entire layer 1 is actually processed by the accelerator card itself, and then before the packets even enter to the CPU, and then the CPU is then focusing on the higher layers of processing, so basically processing layer 2 and layer 3 of the baseband stack. Then a few words about these different options, how we have seen that, and then what we have benchmarked and studied as well, is that first of all about the local-side acceleration. So local-side acceleration option is basically such that the main part of the L1 processing is done by the CPU itself, and then the CPU offloads certain functions like FEC to the hardware accelerator. And typically this would be a PCI card, as said already, but it can be also integrated to the CPU. We also start to see that kind of approaches as well, that some of these selected functions can be actually located on the same die with the CPU itself. A CPU, of course, starts to become more like an SoC, so in that sense it maybe loses some of the kind of characteristics of the general purpose CPU, as we would be then actually including kind of transistors doing something else than just the basic cloud processing into that CPU. But in general, this is the approach that basically the packets from the radio units, the direction, kind of uplink direction, they come first to the CPU through the NIC card that takes them in, and then the CPU handles the L1 processing and just passes the packets to the accelerator for certain selected functions to be accelerated. Then the inline option is such that for the inline there would be a kind of a smart NIC attached to the server itself, and then the packets are completely handled, and then the front haul interfaces also, front haul network interfaces also would be completely handled by the inline accelerator, and the packets would only then enter to the CPU for the layer 2 processing itself. And in this case, of course, we can free up more valuable CPU cores for kind of higher layer processing, and which actually the CPU is very good in doing as such. The kind of inline smart NIC type of solution, I would say, is kind of means also that we actually can use less costly and I would say less complex CPUs from different vendors actually to do the kind of layer 2 and layer 3 processing only, as we don't need any special functions on the CPU itself. And we have seen that the kind of efficiency and capacity and connectivity of such an inline-based solution is typically better than with the kind of Lucaside solution, where we try to do a lot of the complex processing, typically requiring DSPs and different types of hardware acceleration with the general purpose CPU itself. Then inline, as a summary, so just very briefly, so inline acceleration with the Cloud RAN Smart NIC is seen from our point of view the kind of most suitable approach for RAN deployments, including kind of the highest capacity of mobile networks. So basically, with this type of solution, we can get to the similar levels of capacity and throughput, capacity in terms of number of cells that, for example, one server can process, as we would be able to do with the purpose-built hardware for such deployments. Whereas the Lucaside acceleration still lags a bit behind in terms of performance and capacity, but it can be good enough if the requirements as such of the kind of traffic profile that is needed or that particular cell site are not that high, and in that sense, of course, if Lucaside solution can do it well enough for certain rural deployment, for example, then that can be the way to go as well. But as said, so we see that there are definitely some advantages in the inline acceleration solution, enabling higher capacity connectivity, better energy efficiency, and overall lower comparable TCO for the solution. And then also kind of offering the flexibility of being able to select the server platforms from different vendors and with the different types of technology as well. There is a white paper actually that has been published about this from Nokia, and also we have earlier published some information about the Cloud RAN deployment options as a white paper in OCP as well. Then OpenEdge as a platform. So OpenEdge, as I said, so would be the OCP platform to be utilized for the Cloud RAN deployments, and it is kind of really, when we started the design, that was the primary target for the whole solution as such. And OpenEdge can do layer 1 low acceleration. It has capabilities for that. It has capabilities for CPRI, eCPRI conversion as such. There, the front haul gateway has been contributed to OCP earlier for that purpose. Then we can do Lucaside acceleration functions, and we can have Lucaside acceleration cards with the OpenEdge platform, and we can have also several different types of inline acceleration cards going together with the OpenEdge platform. And of course, we can also support other types of acceleration like GPUs, for example, for AI/ML use cases that are becoming more and more popular in the Cloud RAN space as well. Thermally and kind of environmentally, as we know, OpenEdge has been targeted from ground up for the use cases for the telecom networks, basically fulfilling the full NEPS 3 level compliancy in terms of all the different requirements as such. Lastly then, call for action. This work is done under the OCP Telco project and actually there under the EDGE project, and there's a white paper that has been done about the Cloud RAN deployment options earlier already. And we are then also continuing the contributions there with the next generation of open edge platforms in the very near future. And I think the next presentation actually is going to be about that as such. So, thank you from my side.
Thank you, Mika. We have a few minutes for questions if there are any from the audience.
Thanks for the presentation. I'm sorry if I missed it, but why is inline acceleration more energy efficient than look-aside?
When we compare the energy efficiency of the different solutions, we of course have to take into account the capacity of the solutions as such. And typically what we have seen and what we have also benchmarked is that with the inline acceleration we actually can service much more cells than we would be able to do with the look-aside based solution. And in that sense, when we are able to, for example, service double the number of cells, even if actually the kind of server power kind of we would need more power actually to run the server itself, the kind of solution energy efficiency actually is better with the inline solution.
So I think part of what you're saying is some of the NFV functions actually are inefficient on the CPUs and take more.
Yeah, some parts of the baseband processing actually don't run that efficiently on a kind of a general purpose server, or general purpose CPU itself, and therefore we do see that there's a good use case for the kind of SmartNIC based approach to actually service this layer 1 function on the server.
Yeah, so just an observation that, you know, a few years ago there was a big push to do NFV, right, where you do all the functions on the CPU. And we're seeing in general, both for this case and other cases, that there's a move to add acceleration cards back into the mix for certain functions that don't appear to work so well in a pure compute environment.
Yes. Not yet, at least. Of course, CPUs also can develop further, and we will see what the future will bring us. So, yeah.
Right. Thank you very much.
Okay. Thank you.
All right. Our next speaker is